Hi, my name is Sophia. I'm a sophomore. I'm planning on being a nutrition and potentially a chem major. I was in LA for 102 this past semester and I loved it, so I would love to do it again. I found it super rewarding to work with students on challenging problems, give them advice and encouragement as they studied for exams, and find new and creative ways to explain problems to them. In terms of helping students develop their studying learning strategies, I always encourage students to learn the material deeply, because if you can explain why you're doing what you're doing at each step, then you can be a lot more confident when you're taking exams. You can rationalize your way through the answer instead of just memorizing a bunch of steps that you could get confused on. So in my review sessions, I always like to ask students, okay, well, why did you pick that? Or what would happen if you changed this to this? And oftentimes, that would force students to think about the content a little more deeply, or it would signal to them that, oh, hey, I actually don't know this as well as I thought I did, even though I got the right answer. So anyways, I'm going to do a problem from one of the practice exams in 102. It's a titration problem, and it is asking what is the pH of a solution if you add 8 mils of NaOH to it. And for reference, we've got 10 milliliters of a 0.5 molar solution of weak acid. So the first thing that I would ask a student is, okay, what kind of equation are we going to get if we're reacting a strong base, right? This is NaOH, a strong base, with a weak acid. And hopefully they would say a neutralization reaction, right? Because if it's a strong base, it's going to just want to completely react with that weak acid and take its proton to make water, and then also the conjugate base. So anytime we see strong base and weak acid, think neutralization, signaling complete arrow, complete reaction to get water and the conjugate base. Now, because this is a completion reaction, right, we're neutralizing something, are we going to use a Rice table or a BCA table? Right, we're going to use a BCA table, which uses moles, and we're doing this because we actually know by how much we're changing, right? The OH here is going to be our limiting reactant, so it is just going to take away as many protons as it can from that weak acid until it's completely reacted with it. So it's just going to use it, we're just going to use it all up basically. So we are going to do a little math to get moles, fill in our BCA table, and we're left with 0.001 moles of HA and then 0.004 moles of A minus. So what kind of solution is this now? Right, it's a buffer solution because we've got weak acid and conjugate base in approximately equal amounts, right? They're in a 1-to-4 ratio, which is pretty good. It's less than 1-to-10. So because of that, what kind of equation are we going to be using to figure out the pH, given that this is a buffer solution? Right, we're going to be using the Henderson-Hasselbalch equation. So when we plug all those numbers in, we get that our pH is equal to 4.8. And then I always like to ask students, does this answer make sense? So the reason it does make sense is because at our midpoint, remember, our pH is equal to our pKa, which is 4.2. And that would be like over here, right? That's our midpoint. If we keep adding strong base to our solution to make more conjugate acid, or conjugate base, we're going to go up a little bit, and our solution's going to get a little bit more basic, right? We've got more conjugate base than we do weak acid. So it's good that we got a pH that's a little bit higher, a little bit more basic. For these problems, I think it's honestly really helpful to draw it out. So, instead of 0.005, I wouldn't recommend doing this on the exam, but for learning, draw it out. If we've got 0.005 moles of HA, we can sort of say, okay, we've got 5 moles of HA. We're dripping in our OH minus, right? Here's 1, 2, 3, 4. It's going to react with 4 of those. So then we get 4 conjugate bases, and we're left with only 1 weak acid. So that's why we've got a buffer solution, which are these two equations. And this one, this bottom one, is working a little bit more because we've got more of our conjugate base, making a little bit more hydroxide, which is why we're getting a slightly more basic solution.